press *0.
There are 17
parties in conference, including you.
And I'm not sure if I can speak. This is Xiaowei Kwan at Boulder, ESR.
Anyone else on the phone?
Yes, I'm Tao Zhang from NOAA PhD.
We have a number of staff here from the Lower Colorado River Authority in Austin, Texas.
And this is UCI from Solutions Group.
All right, good afternoon, I guess, some people's time, and good morning in the West Coast.
Okay, if that's it on the phone, I'm going to throw it over to Kingtse to give her presentation. Kingtse Mo joined NOAA back in 1987. She's working at the Climate Prediction Center since that time. She started building drought research at CBC about 3 years ago, and she currently gives the Drought Briefing, which she's actually missing to give this talk today. So thanks, Kingtse, for
Can you see my presentation?
What's that?
Can you see my presentation?
We can see your presentation, that's right.
Yes.
Okay, good. So I will start.
Sure.
Okay. As you know, CPC gave monthly drought briefing. Actually, right this moment, my colleague, Dr. Chen, is giving it since I'm here. Basically, we review hydroclimate conditions for the past months and show the nowcast. And then we also show the seasonal forecast for drought indices for the next season. This information is used by Drought Monitor authors, Drought Outlook forecasters, RFCs, National Weather Service field offices, and some local government water resources managers. This also gives a forum that for the person or people who generate products and users, they can exchange information to improve that. It's almost impossible to do drought briefing if not because of your support. In particular, University of Washington and Princeton University. And this is a CTB project, and Dr. Enrita wanted me to talk about it. So, basically, this project joined by Eric Wood's group from Princeton University, Dennis Latimio's group, Eric Wood, Princeton University, Latimio's group, University of Washington, Michigan State, Li Fang Lu, and EMC, Michael Eck and Yulan Xie, and us. For both monitor and prediction, we are focused on drought indices. For the meteorologic drought, it's no problem. It's a SPI we can do from Ping sheets, global precip analysis. And for that, we also cut to the United States. But for the stream flow prediction or SI index or agricultural drought, total soil moisture, we don't have nicely graded data, so we use NLDAS.
Pick up the phone.
Yeah?
Everybody on the phone, please mute besides Kingtse.
Okay. I'd like to share with you the accomplishments and future plans. Certainly, we love your input. For the monitoring, there are two groups produce near real-time NLDAS system. But if you look at the day in, day out, you will see they have systematic differences.
Push the button. Yeah,
so we like to quantify them.
This one.
And at this time, also, UW wanted to generate to a much finer grid for the later NLDAS development.
Thank you.
The case in point, the case in point is that if you look at the screen, this is January soil moisture percentiles for the EMC and the University of Washington. At the time, the Texas drought just began, and you see they got that. But if you look at the southeast drought, they both show dryness. And you're also looking at Dakotas, California, and Northeast, they all show wetness. But if you do the classification, they are quite different. University of Washington is more intense. So UW and us did a assessment project to see where the difference comes from and whether we can do something about it or we don't want to do anything because this just shows the spread. We basically calculate RMS between two system ensemble systems. You will find that in the eastern region the difference is small, but for the western region it's pretty large. Other times more than 20% percentile of soil moisture. That means it's too large for drought classification. If you look closely, the most difference are over the western region. And also, it is after 2001 when NCEP start to use, the NARR start to use real-time precip analysis rather than historical analysis. And later, of course, both NCEP and UW went to near real-time, so all the data were taken from real-time analysis. That caused the difference. To pinpoint to see which forcing is more important, we separate the forcing in the precip alone and the F forcing consistent, both the difference in temperature and the winds. You will see immediately if you keep the F forcing the same but use different precip forcing, then you can see the difference very large over the western region, almost as large as I just showed you the previous slides. But if you use the same precip forcing but use different F forcing, including the surface temperature, the difference is very small. So basically, the problem is because the report of real-time stations. You will see in the historical period, there are a lot of stations over the western region. But for the real-time period, there are very little. When you don't have very good coverage, then how you use the station, the location, how you do the analysis will make a lot of difference. So basically, we really need better forcing. Since this is the difference of analysis rather than some other problem, we think we just will use that as a spread. So we know the difference between the two NLDASs and know how trustworthy those features are. For the drought forecast, the milestone was when Princeton University transformed their prediction system to EMC, and ULA has been running systematically each month to provide us the seasonal forecast. And the University of Washington has been doing that for many years. Eric's group also evaluated CFS V2 and compared with CFS V1, and their most recent urgent task is transfer the system to use V2 rather than V1, since V1 may stop. There is a possibility for it to stop in next year, June. So this is an example for the current forecast. The forecast was made using October initial conditions. You can see the Texas drought, Oklahoma-Texas drought in the southern plains will continue for next 3 months. It also shows the drought, unfortunately, is going to spread northward. But the good news is southeast drought seems tapering off. So this type of forecast, very important for the forecast, will be their first look of the season coming up for their drought seasonal outlook. Now, Princeton University has been evaluating CFS-V2. The message is V2 for the first month lead for both precip and temperature and better than V1. However, the multi-model ensemble is still far superior. This means, like right now, climate test bed, Dr. Jing Wang has been encouraging us to do multi-model ensemble, and I'm really looking forward to the improvement once we use the multi-model ensemble prediction. About last year or so, with the Princeton University, CPC has been developed a SPI forecast that is in operation. That has been in operation since April this year. This again is a current prediction. Again, both of them, just like the soil moisture prediction, it shows a certain plant drought. It also shows it's migrate northward. They also show in the northeast, it will have above normal rainfall. And this, again, the difference among those predictions will give forecasters the spread so they can engage the trustworthy. Another thing very important is four institutions have been working on research projects which will show what is more important to the drought prediction, so we know where we should focus our effort. I will show, first one is Shukla and Ladimai's paper. They measure, they consider the importance of inertial conditions relative to the boundary conditions, and they show inertial conditions are more important for the month 1, and even the month 2 or 3, it shows some scale. And secondly, is I will show you a next slide in a minute, is UW working with Randy Costa's group to show how the importance for the snow or soil moisture inertial conditions. Currently, CPC and UW are working on how is the best way to use daily forecasts to improve the seasonal drought forecast. At this moment, both Princeton University and UW have been using monthly means. They're not using the daily forecast. So we will see whether if you use daily forecast, scale will improve. This project is ongoing. Princeton University at this moment compare the scale for V1, V2, and the ESP. That means ensemble stream flow prediction for river charges, and also they assess the scale for ongoing the NIDAS pilot project over the southeast. It just demonstrates the importance of snow and the soil moisture inertial condition for seasonal prediction. And basically, for the spring, when you have a snow melt, this it will be very important. And also, this is the time soil moisture still start to increase and get into the reserve for the whole year. And for the April and even to the summer, the snow is very important. But for the other months, you need to know good soil moisture to enhance the forecast. Basically, I think this demonstrates CTB project, at least for this, for drought prediction and monitoring, is a big success. Both EMC and CPC, we're working closely, and also we're working very closely with UW and PU to develop monitoring and prediction. So I'm looking forward to continue to working with all those groups, and also those in the audience. If you like contribute something, or you like to working with me, or you think a drought briefing can improve, or you want a copy of a drought briefing PowerPoint, you can email me. I'm happy to working with you, because the drought prediction and the monitoring briefing is for you. And well, I ended there. Thank you.
Okay, thanks a lot, Kingtse. Again, we're going to hold questions until the end, and I just want to remind everyone on the phone to please check mute. There was I think it sounded like a group who maybe doesn't have mute on their phone during Kingtse's presentation. So next, we're going to switch over to Mike Ack. Just got to get him.
Yeah, we're getting our presentation up right now. Is it on the bottom? There we go. Right here. No, other one. There we go. Okay.
And they go to slideshow.
Yeah.
Go to slideshow from beginning. Okay.
Okay. Can people see?
No, Mike, you're gonna have to click share my desktop.
Not yet.
Sorry, we're new to this too. No. Cisco Web Manager, I think that's it. Share my desktop. There we go. Thanks. We're cutting into our time, I think. Okay, and now go ahead and do it as a slideshow.
Okay.
Yeah. Okay, how's that?
Looks good.
No?
Okay, I still have Kingtse Mo as the one.
Yeah. I don't see you.
I can see you. That's weird. I can see it, Mike.
You can. Oh, Chris,
Yeah, I can
on
see
here.
it.
Very good.
How come I cannot? That's weird.
Kingtse, you have to go back into the meeting center in order to...
Oh, okay.
Go back.
No. She does. I mean,
okay.
Everybody could see us.
Okay.
Go ahead and start the session.
Okay, done.
Okay.
Okay.
Go ahead, Mike.
There?
Yep.
Yeah.
Okay. Well, there's two shorter presentations that we'll have, which is kind of a summary of our current status. Whereas Kingtse was showing some of the nice drought results. I guess we're more the science and engineering behind some of the products then that she uses. For example, NLDAS, the North American Land Data Assimilation System. You'll see NLDAS thrown around quite a bit. And what we're trying to do is improve that system, and there's a couple of different things we're doing. Like I said, Krista and David, if you're in here, jump in because you're the list experts and so on. So one of the topics was assimilating snow and soil moisture data into the system. Let me back up just a little bit and say the NASA Land Information System, I mean, you can read it across the top. Can people hear me okay? I'm a little far from the phone.
Yeah, we can hear you.
You can hear me, okay. Okay, there we go. Maybe that's a bit closer. As Krista and David have put together, it's a flexible land surface modeling and data assimilation framework. And part of our NLDAS currently that we're trying to transition into operations, we plan to transition into operations, has an older version of LIS working for part of the model. But what we want to do, and this is working jointly with Krista and David and company, is transition our whole NLDAS to work under the LIS framework. What is nice about this? We can do parallel processing, and we can, greatly speed up any kind of, I guess you could call it reanalyses that we do, where we go back and run the land models offline or uncoupled for 30 years to build our climatologies. And so this is a very powerful framework under which, in which to do that. The other thing, and that's I think in the title of the talk, is we can assimilate data, and you can see by oh, wait a minute, I can actually use this. Can people see my mouse?
Yeah.
Oh, okay. Oh, that's right. This is
your desktop.
It's my desktop. Anyway, this whole framework shows how running the land models, optimizing the data, assimilating data will help improve then the land model predictions. And from the drought aspect, ultimately that helps us improve the soil moisture, soil temperature, other land states, and runoff. And so the full hydrologic budget then. And that's basically what you saw from Kingtse's talk, the different metrics that they look in with runoff and stream flow and soil moisture as well as precipitation. So I will say, David or Krista, once again, jump in if I'm skipping over something. So let's go to the next slide. Here we go. Okay. So the other nice thing about LIS, the Land Information System from NASA, is the fact that we can use a much more updated version of our NOAA land model, and as well as SAC, as well as VIC, and catchment model. Mosaic is an older version of the NASA model. Currently it's part of NLDAS, but we'll upgrade to a later version. So this particular framework allows us to assimilate soil moisture and snow products to, again, better characterize the initial conditions of the soil as we're monitoring them for drought. So the various parameters and spatial resolutions and satellites are given at the bottom here. The important point to remember is we're bringing in a data set that represents reality rather than just letting the model run unconstrained, I guess you could say. So the fact that we have a lot of remote sensing data available to us allows us to make a better initial condition. I should point out, well, I won't point that out now. there's going to be some more data coming online as well. Let me see. Click. Here we go. Okay. Recent data simulation results using NLDAS and LIS. Referring to a paper that Krista had submitted. I can't see. I have to move something here. There we go. Okay. So essentially, this is demonstrating, well, just how does data simulation help us? And in this case, we're talking about soil moisture. In this case, from AMSR-E. I was going to mention in the future there's a SMAP product that will be coming out. I won't bother with the acronym. The Europeans have a remote sensing soil moisture mission that is flying right now, providing data that we will try to use to further improve our land states. But suffice it to say that using the simulation improved the characterization of the surface, and that resulted in a better prediction of, in this case, I think we're showing ET, is that right?
Yes, ET.
Yeah, okay, thank you very much. And this is March, April, May time frame. So you can see a lot of business going on over the lower Mississippi Valley and up into the Midwest. So on to the last slide. Oops. Maybe I'm not doing this right. There we go, last slide. This is one David said we could skip, but I think it's important to point out that there is a lot of data out there for LDAS, and NLDAS is the part over North America. Broadly speaking, I think there's global data as well. But suffice it to say that this data is available for people to look at, and it represents a long-term climatology. And what you're seeing along the bottom here is just the characterizations of what's available and how to get it. There also is an NLDAS website at NCEP as well, and that's mostly the things that are being produced in a pre-operational sense, the land states, soil moisture, runoff, etc., to then feed the drought prediction, feed the drought monitoring, and part of the tool set then that Kingtse and others draw upon to help with the drought assessments and forecasts. So NASA, LIS, data assimilation, run our land models more efficient, and that's what we're after in that project. And so I guess if people can remember questions, I'll jump over to the second thing. No, next one over there. I think that's it. Yeah. There's a few more slides here, so maybe we'll go quick. This is also an NLDAS-like project. That is, we drive models offline with observations to have the land states evolve so we can see how does the soil moisture change, how does the temperatures change, what are the evaporations, what are the runoffs, and so on. But this is work by Jairi Dong and Brian Cosgrove. Jairi Dong is at EMC, or NCEP EMC. Brian Cosgrove is up at the Office of Hydrological Development up in Silver Spring, and Kingtse and I are working with them on this. This is a continuation of some earlier work that Jairi had worked on and shared with OHD. Essentially, it's like our NLDAS, which is run at 8th degree, but this is done at the much higher resolution of 4 plus 4 plus kilometers. That's definitely of interest to the hydrological community, and we kind of see it as the spearhead for where we want to go ultimately in our NLDAS work. I'll mention that the systems are currently running under a version of LIS that we'd like to upgrade to the latest version 2. So it kind of goes hand in hand with what's being done by Krista and David and their group up there at NASA. So moving on, this is very long, a lot of details. Essentially, Jairi spelled out a lot of the work they were doing. The one important aspect on this work going to anything high resolution is how do you get the right forcing data? Because the forcing data may come from a lower, or does come from a lower resolution set of data. And so forcing data is solar radiation, temperature, precip, winds, humidity, etc. And the one thing that we do, the current focus of the data is, well, how do we downscale the current NLDAS forcing to then drive the land model at a higher resolution? And in this case, he's running the NOAA land model, which comes from NCEP and other partners working on its development, as well as the SAC model. So, I should mention one of the other things is the spin-up strategies, because when you first start running, say, a 30-year climatology, how do you more properly spin up? What states do you start from? 50% saturation, completely dry, completely wet. There's different ways to do this, and that will be that has been a topic in the past on some previous work that will feed into improved spin-ups. But right now, Jairi and Brian just wanted me to share this downscaling, the downscaling of the NLDAS data, and we're particularly interested in how we're downscaling the temperature. Right now, there is an adjustment based on terrain where it takes a temperature from a source like the North American Regional Reanalysis, the real-time extension of that, that's run at 32 kilometers, that feeds actually NLDAS, but it also feeds this work here. The problem is, how do you take it from a lower resolution that has a terrain that may be different than what a high-resolution terrain is? And so the issue is, how do you take a temperature from that and scale it or rescale it to be appropriate for the higher resolution? Well, you're going to have to move, say, an air temperature up or down depending on, say, a standard lapse rate. Well, we found that that's maybe not quite an efficient way to do things. So this is just more detail on the deliverables, and this is, of course, going to be available. I guess, Dan, these are going to be available to people, yes?
Yeah, we're going to try to distribute them. We haven't figured out the system.
Or have a site for them. Anyway, it's just a deliverable schedule. And the point is, there's a lot of data that we're using from a number of sources that is going to help, that's helping us to look at, well, how do we make this lapse rate adjustment so that we can have better forcing at the higher resolution? And Jairi and Brian were just outlining all the different places, say in the West, where there's the biggest adjustments needed based on elevation. And he's noting the snowtail sites, more typically higher elevation, and the, I'm not using my mouse enough, I guess, and the U.S. Historical Climate Network sets as well. You look at this topographic map, and this is the resolution at the 4 kilometers. It would be a little coarser for NLDAS, which is 8th degree, and it would be even coarser for the North American Regional, oops, it jumped, Regional Reanalysis. Let me go back. Oh, here, there we go. It's coarser at the 32 kilometers. So something interesting that Jairi found in current work, previous work, and now extending it to current work, is 6.5 degrees, and people see my cursor moving along here?
Mm-hmm.
Yeah. 6.5 degrees was the standard adjustment when you're going 6.5 degrees per kilometer, when you're moving from one lower resolution data set to a higher. So the elevation is lower or higher. You have to adjust it one way or another. But we can see we've stratified the data by different states, and you can see Montana, Wyoming, Colorado, etc. And it's stratified by month of year as well as the station. And then over on the that's left-hand side. On the right-hand side, you can see California, Oregon, and Washington. And what's notable is it shows a characteristic difference between typically maritime and typically continental systems. And the one thing he also noted was as you go from north to south, you're going to be getting a different character on this lapse rate. Why is this important? Because if we make appropriate adjustments to the forcing data, it will affect then the subsequent evolution of the land states, which is what we're trying to characterize more properly. And in the West, this can be particularly important, especially if you have big mountain valley differences, and there's big terrain differences that would occur over a smaller scale than you would see anywhere in other places. So he further divided things up into this network of 2.5 degrees by 2.5 degrees boxes to just see if we could get a better characterization of this lapse rate adjustment. And I contend there might be, there's a temperature signal in here, there might be, say, a moisture or dew point signal in here as well, because certainly as you go further inland, typically you might think things get drier. So he further divided things up that way.
Mike, just about 1 minute left if you could.
Okay, I think we're just about done.
Okay,
anyway, with all the data, he stratified it, and as a first go, we have a better characterization based on the air temperature and the lapse rate that you get to the air temperature and the lapse rate. So instead of using a standard lapse rate, we'll use a lapse rate that's more dependent on this temperature reference. But anyway, we're exploring that further. Again, better characterization of the land of the downscale data for our system. Just to show you really quick, the NLDAS on the left is the current system that ULong is running, and the HRAP at the 8th degree resolution, and you can see the finer character of the resolution in the higher resolution HRAP grid. I'll jump to the last. These both represent 30-year climatologies, by the way, in the soil moisture. This is just further statements about what I had said about the lapse rate adjustment is important for downscaling the data, and we'll just keep proceeding with the other phases of the HRAP work toward the end of better characterization of the land surface at a higher resolution, and again, that feeds into the drought community and, for example, the things that Kingtse summarized. So we work on the engineering and the science behind then the products we feed to her. And it cycles around. Anyway, I guess that's it.
Thanks, Mike.
Thank you.
Mike. Okay. So we're going to take the presentation back, and our final talk is by Martha Anderson. Martha is a physical scientist at the U.S. Department of Agriculture in the Hydrology and Remote Sensing Laboratory, and whenever you're ready.
Okay. So I've been working with Chris Hain and Zhu Zhan at NOAA NLDAS for some time now on developing a new kind of drought index based on thermal remote sensing of evapotranspiration. And part of this project also involves investigating the relative utility of assimilating both a thermal kind of soil moisture proxy and a microwave-based soil moisture proxy into a prognostic modeling system like NOAA NLDAS. So that's what I'll be talking about today. So just a quick refresher on the difference between a remote sensing approach where we do energy balance and the water balance approach in a model like NOAA and the NLDAS models. In the water balance approach, you need to know the precipitation, and you need to know the precipitation as your primary input, and then it models all the flows of the water through the system, and that's really useful because we can learn about the runoff and the drainage and such. But the challenge is you need to, of course, specify a number of parameters across your modeling domain to get the partitioning right. And those are sometimes difficult to specify accurately. And also importantly, you're relying on the accuracy of your precipitation inputs, which is pretty good here in the U.S., but in some other countries where we don't have the rain gauges, Doppler radar, Africa, for example, it's more problematic. So in contrast, in the remote sensing approach, we don't need precipitation as an input, and we really don't need to know much about the subsurface soil characteristics. In this case, the evaporative fluxes are being diagnosed from the land surface temperatures that we can obtain from these satellites in the thermal wave band. And we're taking the energy balance approach. We know how much energy is being put in the system from the insolation, from the long wave atmospheric radiation. We can solve the energy balance.
I'm sorry if I can interrupt. I don't see any of the slides on my...
Yeah, neither do I.
I cannot see either here.
Yeah, sorry, I just sent a little private message to
Maybe
Dan.
share your desktop.
You just share the desktop, please.
I'm guilty of not sharing my desktop.
There we go. Okay. Now we can see. Thank you.
Okay. Well, I hope you can visualize all that in your heads. So there's the water balance approach, and
now we can see. Okay, good. Thanks.
Thanks for
thanks for letting us know.
Glad I didn't get through the whole talk.
Okay.
So very, very independent means of coming up with the same kind of information. In the remote sensing approach, we're very narrowly focused on only ET, and so I think there's some good synergy where we can use one modeling approach to kind of check and complement the other modeling approach. And I'll just give you a few examples of where the remote sensing has kind of a leg up on a prognostic water balance model. This is a irrigated region in the southwestern U.S. in Arizona. If we wanted to get the evaporative fluxes from this region from a prognostic model like NOAA, we would have to know a priori that this area is being irrigated and what the seasonal rate of application is. So remote sensing, the land surface temperatures are telling us without any a priori information what's going on here. Another area, and these are areas where the evaporative fluxes are not well correlated with the regional precipitation pattern, as you would kind of assume in a standard water balance. We're seeing enhanced ET in our remote sensing in areas of very shallow water table, which may be due to extraction of water by free epiphytic vegetation, or maybe enhancement of the direct evaporation from the soil. Again, to build in this sensitivity into a NOAA model, you would have to couple that with a model of the groundwater table. But we're getting that information from the land surface temperature signal in the remote sensing approach. So there is some complementarity here that we want to try to exploit. The model that we're using is known as ALEXI, for Atmosphere Land Exchange Inverse Model. And it has been designed very specifically to exploit the high temporal frequency information we get from the geostationary satellites. We actually use a time differential temperature signal, the morning surface temperature rise, as our main driver, and that makes us much less susceptible to errors in the retrieval of the absolute temperatures. The surface temperature constrains estimates of sensible heat flux off the land surface, and then we compute ET as a residual. So we can run this at a regional scale using geostationary data, but if we want to have finer resolution flux maps, we can perform a disaggregation with a technique we call BIS-ALEXI that uses higher resolution temperature and information from polar orbiting systems like Landsat and MODIS. And so we can kind of end up with a multi-scale system of consistent fluxes going from the global using the international suite of geostationary satellites to GOES east and west over CONUS, down to MODIS at the basin scale, and then Landsat. I'm in USDA. We really like Landsat because we can see fluxes from individual farm fields. So this is giving us estimates of actual evapotranspiration. To get a drought index out of this, we've been exploring something we call the evaporative stress index. It's been around for a while as a concept. We ratio that actual ET with potential ET we would expect under non-moisture limiting conditions. So it's a normalized variable. We find the normalization to be very useful because we're kind of normalizing out some of the variability due to radial forcing and focusing more clearly on the soil moisture drivers of ET. And then we compute standardized anomalies in that unitless variable. And here are some maps of various drought indicators. Seasonal anomalies, 2000, 2009. On the left are anomalies in U.S. Drought Monitor classifications. The second column is this thermal-based evaporative stress index. This is my little mouse keeps disappearing, standardized precipitation index, and soil moisture and ET anomalies from the NOAA model. So you can see that the thermal-based index really reproduces the spatial patterns in the drought pretty well, with the advantage that we needed no precipitation data to derive that index. So they are very independent indicators. You know, the current thinking is to use a convergence of evidence from multiple different drought indicators to really establish if it's a viable drought signal. And so this is certainly independent. just a closer look at some monthly variability in these indices, we find it really correlates very well with the soil moisture anomalies from NOAA. So this is 2002, where we had the big drought in the west, and 2007 with a drought in the southeast. And I will just zoom in here, seasonal anomalies for 2007 from the Drought Monitor, from soil moisture variable from the NOAA model, the prognostic model. Down here is a soil moisture retrieval using microwave data, and then the thermal-based drought index. And you can see how well the soil moisture from the NOAA agrees with the thermal data. We can get a little better, higher spatial resolution, and also this is going to be very easy to transport to other countries where we don't have the good precipitation data. Interestingly, the microwave product missed the drought in the southeast in 2007, and that's because that's a really densely vegetated area. The microwaves from the soil surface are, we think, being absorbed in the water contained in the vegetative canopy, and you lose the signal there. But in the thermal band, we're seeing the stress of the vegetation. This is my hypothesis. The canopy is stressed, the leaf temperatures are elevated, so we get a thermal signal there. But there are advantages to the microwave approach. You can see through clouds with the microwaves, and we're relying on clear sky conditions to get our thermal retrievals. So that's going to be very beneficial in areas like the Amazon, where you don't get a lot of clear sky views even with a geostationary satellite. So that's why we're investigating the utility of kind of merging these two moisture data streams in an assimilation system. We get higher resolution in the thermal. We also seem to be sensitive to a deeper volume in the soil profile, because you're kind of sensing, at least where you have vegetation, you're sensing moisture down in the root zone, whereas the microwave retrieval is only a couple centimeters. So this is work that Chris Hain has done. This is a data denial experiment where he's forced the NOAA model with a degraded precipitation input data set, and that's the black line on the top. And these are root mean square errors in soil moisture in various layers in the soil profile. And then we are sequentially assimilating a thermal, the red line, microwave, which is the green line, and both signals, the blue line, to see how the errors improve through the assimilation. So in the surface layer, 0 to 5 centimeters, it looks like the green line is winning, and it does a kind of a better job than the thermal assimilation. But as we move deeper in the profile, here they're kind of have somewhat equal skill. But in the root zone, the thermal model is contributing more to the decrement in the errors, and this is on average over CONUS. We also find spatial patterns in the kind of the added skill of these various inputs. The microwave tends to have better skill in the west, where we have sparser vegetation. The thermal has more skill, relative skill, in the east, where we have a lot of dense vegetation. So we're working on seeing how we can kind of optimize a dual assimilation scheme based on these findings. Let's see, advance. Seems to kind of, there we go. So if I have a few more seconds, I'm going to give you a couple more examples of where the thermal remote sensing seems to have a lot of benefit. We're doing some comparisons of prognostic and diagnostic ET over the Nile River Basin to see if we can provide some improved hydrologic information for the Nile Basin states, and this is in collaboration with people at Johns Hopkins and at NASA Goddard. So this is a 6-kilometer ET map that was generated with Alexa using Meteosat second-generation data at 6 kilometers resolution, and you get a lot of nice structure. If we're going to do some disaggregation using Landsat, trying to look at the distribution of water in the complex irrigation canal systems that develop along the Nile River Basin. And so here is a composite of daily ET from Alexi and in this normalized ET over a PET index that we use in the drought monitoring. And there's a couple features here that are of interest. One is that we're sensitive to the enhanced ET up in the Nile Delta, which is a heavily irrigated area. And we also see evaporation from the Sud wetland, which is in down right here, which is a major loss of water along the White Nile as it goes up towards the Mediterranean Sea. And these are both features that are missing in a standard NLDAS model because they are not related to precipitation patterns. And so this is why we think that comparison of these two modeling techniques is going to give us some useful information. If we want to know about the seasonal patterns of water use in the Nile Delta, you can see the NLDAS model as it normally runs has no signal there. Now, Johns Hopkins and some collaborators are working on an irrigation submodel, but essentially you have to know what the irrigation is before you can implement the submodel. But I think the remote sensing can help to guide that. And but in other parts of the domain, the two models agree reasonably well. So, and here we ran the drought index over the Horn of Africa, and we see a pretty good signal over that area where the famine in Somalia is occurring right now. So that is the conclusion of my presentation.
Great, thanks a lot, Martha. Okay, so thank you to our three speakers and everyone on the phones for being a guinea pig in this webinar experiment. We have some time for questions, about 10 minutes or so. So we'll start in the room. Does anybody in the room have a question that they'd like to pose to the speakers? Rick?
Given Kingtse's early demonstration of the sensitivity to the distribution of precipitation stations in the West, I'm wondering how Martha's work on remote sensing might be used to help solve the problem that Kingtse was demonstrating.
Well, and in fact, Kingtse is a collaborator on this project. So we're going to be delivering. We're starting to deliver right now real-time remote sensing-based ET maps to Kingtse for comparison with the prognostic estimates. And we're doing a detailed intercomparison of those products as well. So I think they will be very useful.
This is Mike Eck. I'll echo that as well and say that I think this greatly complements our prognostic models, and especially in areas, as you said, are irrigated or have other sources of water that are not precipitation. That assimilation of such data would really be helpful, because then these models are used as initial conditions to, say, kick off seasonal forecasts and so on. So anyway, this is very encouraging.
Yeah, I just wanted to say that Ping Shi at the CPC, right now they are working on to combine gauge data and the satellite data and radar data together to see if they can get a better precip analysis, because we saw those differences because both University of Washington use index station and CPC, they are just based. So if the station they are not coming in, we are the luck. But if we combine with the satellite and also they are looking into the radar data, then they hopefully, especially like over West, there's almost no station there, will enhance the precip analysis. And since NLDAS quantities are very dependent on the precip quantity, I think that in the next couple of years we will have a better precip analysis that will also improve the NLDAS quantities.
And indeed, your thinking may go beyond just looking at precipitation in a sense, since the satellite information provides other kind of information. It might occasion a rethinking of how the prognostic models are actually used. Thank you.
Any other questions in the room?
Hello.
Questions on the phone?
Yeah, this is Yulong from NCEP. I added one comment for Mike presentation final resolution about air temperature. I think is a main point, another main point, if you have the good surface air temperature, and then all the land surface model separate precipitation, total precipitation into the snowfall and rainfall. If this is the temperature is quite very accurate, then you can accurately separate rainfall and snowfall. This means for the higher mountain area, you can simulate the snow-related process is very accurate, and also you can simulate the seasonal cycle for stream flow and everything, evaporation seasonal cycle, everything is right. This is one comment. And the second question, I actually worry about ET evaporation. Now I did some work evaluation about ET in NLDAS. I find I have no reference data set. Even for the tower unfree flux data, still they have the energy non-closer work. I find the ET is not accurate. My question is from Crystal and from Max Anderson, do you have any idea to evaluate ET?
Well, if you apply a closure correction to the eddy covariance, they're getting better at closing the budget. I think typical closures are kind of on the order of 85% or so if the people running the instruments know what they're doing. So I don't think it's that big of a problem, but the problem is that you can't compare a 20-kilometer model estimate to a tower flux and expect to get a really good validation of your model. So that's where incorporating some of the higher resolution satellite data like Landsat, getting down to the scale of the tower footprint is kind of a useful tool. But, I mean, you are correct that there's no wall-to-wall gold standard for evaluating ET data products.
Yes, and this is Krista. So related to that, and I agree with what Martha said, but just in addition to that, in the result we showed, we're using some new reference ET data sets that are based on remotely sensed data and or tower data that is gridded on a quarter-degree scale. And that's the MODIS ET product as well as the LandFlux, or the Young et al., the Max Planck Institute gridded FluxNet data set, which, you know, without getting into details, they went through a whole exercise about how to properly grid flux tower data because it is a point-to-area problem. So those are the references we're using now, but I think the thermal work is an important part of that.
Yeah, because Krista, I just use tower data to evaluate. Also use your data for MODIS and global FluxNet from Martin Jones. I find this is compare. I evaluate with the basin scale ET. You know, I have the precipitation, also I have stream flow. And then for the multiple years, I can get the ET, estimate ET from P minus R. Okay, and I look, this is a problem, and I find the MODIS is underestimate from the reference basin scale ET. I don't know now which method I can use, and then I raise this question to you.
Right. Well, I think the point Martha was making in her talk and the point we've followed in all of our work is that there's no one gold standard. Okay, you have to think of it as these are members of an ensemble of ET estimates.
Okay. Absolutely.
And that's how we think of it. It's all part of our uncertainty analysis to consider each one of these as a multi-model estimate of ET.
Yeah, well, multi-model.
Or multi-approach, I should say.
Right. Yeah, that's a good way to.
Yeah.
Point measurements, spatial measurements, remote sensing, in situ, and et cetera. So I think of land surface measurements in terms of fluxes of, scintillometry, which has some certain theory behind it, but it's an integrated, like 1 kilometer estimate. Not to mention cosmic from Jim Shuttleworth and so on, which gives you a bigger spatial field of soil moisture. So suffice it to say, there's a lot of different measurements, and no one kind of owns the show, and we have to integrate them all in some manner.
Right.
Absolutely.
Yes, agree.
Yeah, and I think Kingtse's talk also highlighted the value of having these multiple ensemble members, you know, for any quantity, not just ET. So I think,
exactly, I agree.
You know, this is kind of like a big summary lesson for all this, the drought work we're all doing. We need these multiple approaches to deal with this. There's all the uncertainty, and, you know, you're dealing with an extreme situation. So when you're dealing with extremes, it's even more important to have multiple ensemble members.
Okay, well, we've arrived at 2 o'clock, so I think we should call it quits for now. I'd like to thank everybody for joining, for our 3 speakers who are giving presentations today. And ask that everybody come back on November 8th. We're going to have the next MAP webinar on regional climate modeling. So thanks, everyone.
Thank you.
Thank you.
Thanks very much, Dan.